Okay, so we'll get started. We've got some stuff to get through today. Welcome back, and we will start with some announcements just to take a look at where we are in the semester. So today I'm going to try to finalize the chapter on cache hierarchies. And the accompanying programming assignment 5, which was all about cache hierarchies, is now out. And after today, there should be enough of the material that we've talked about to make sure that you can work on programming assignment 5. Our next chapter is going to be the final chapter, which is on digital logic. So this is basically, now that we've looked at how high-level programs turn into assembly and how that runs on the CPU and on the memory and how the memory hierarchy ties it all together. The digital logic portion of this class talks about how, gives a really quick preview of how electronic circuits build up the ability to run assembly code, to do operations and so forth. And so the accompanying reading assignment for that, I recommend from the main textbook, CSAPP, chapter 4.2 offers some of the material. And if you're looking for a more substantial text on digital logic, the one I recommend, and it's also available if you go to Rutgers Library, is that you can get the canonical textbook on this topic, which is Patterson and Hennessy, Computer Organization and Design. That book, in the appendix, there's going to be an appendix on the basics of logic design. That would be a good reference if you're going to try to read up on something for the final part of this class. All right. So what we'll do today is first I will give a quick start to programming assignment 5. I'll try to walk you through some of the components so that you can hit the ground running with that. We'll do a quick review of the relevant parts of previous lectures that will help you with programming assignment 5. And then some new material on cache performance metrics and how to write programs so that it works well with caches. Okay, so before I launch into the quick start on programming assignment 5, does anybody have any questions about where we are in class? Yeah, so Julia has a question about the quiz. So sorry about, I know I had previously mentioned that there will be a quiz early this week. I ended up having to focus on making the assignment and getting the assignment released, so I didn't get around to making the quiz, so sorry about that. I'll try to make up and create a new quiz once that's ready. So Michael has a question here. So after today's lecture, you should be able to do all parts of programming assignment 5. So let's go ahead and launch into programming assignment 5, Ren. So programming assignment 5, there's, it's 5 parts to the programming assignment. The material that we've covered before today is enough to get you through the first 3 portions, right? So these first 3 portions talk about having you to write a C program that models what happens when a program runs on a cache, runs with a cache. You're supposed to write a program that models that behavior. And then after today, we'll get around to talking about techniques for optimizing code so that it runs better with caches. And so after today, you should have enough of the material to do all parts of programming assignment 5. Abia says, is this the last programming assignment? No, so there's going to be one more, hopefully shorter programming assignment, which is about digital logic. And of course, I know that this is getting to the tail end of the semester. And so the difficulty and the length of the assignments will reflect that. And there's no final exam for this class. Okay, so programming assignment 5 is also still worth 120 points, just like the other assignments. Yeah, there was a question, I think it was from Darren.
Regarding, so you said there's one more programming assignment, and it's since this one is due on April 26th, it's probably going to be released around then. Will we still be able to have access to like meeting with you and the TAs for office hours if we have questions regarding that, since I think that's also approaching reading days and stuff?
Yeah, so I'm gonna have it so that at least office hours will continue during reading days. So one more question from the chat box. The question is, are there code reviews? So following the kind of general plan for recitations, you can refer to Canvas. We had a on the page that talks about who does what recitations and when. So here's the page. So following this plan, if you want to do code review of the previous assignments during recitations, you can go to Azita's recitation or Niraj's recitations. Those will be focusing on reviewing the previous assignments, and then while the other 3 TAs are covering review for this current assignment. Okay, so let's launch into what programming assignment 5 is all about. So a few high-level things, right? So assignment 5, the amount of code that you should have to write to get this to work is going to be less, definitely. It's going to be less code, less lines of code compared to programming assignment 3, especially less code than assignment 2 and 1. Now, the challenge for you will probably be in trying to figure out how all the pieces of code work together. So this assignment is definitely more conceptual than it is necessarily just asking you to write a lot of C code. Okay, so the assignment description is up, and you should definitely take a very careful read through the description. The setup, which we'll do now, is just like all the previous assignments. So we'll go to our GitHub repository on iLab. The same set of directories that you had cloned from GitHub this time around, we'll update it. So go to our repository, and if you git pull, you'll get the latest files for programming assignment 5. Now, we talked about how the first 3 parts of the assignment ask you to write a cache simulator. And I've broken it into 3 pieces so that these should basically progress from being from the easiest case to the most complex case. And these correspond to different types of cache designs and with different parameters. So the first one that you'll write is a fully associative cache, which should be the simplest to understand among all of these. And we'll focus on how to crack this one today in our quick starts. Okay, so in our programming assignment 5 directory, we have, this lag is really bad. Okay, so this lag looks bad. If it's very, very laggy, I'll switch to a different login. So in the programming assignment 5 directory, we'll first go to the fully associative directory, which is the first part of the assignment. Okay. And your task is to write a simulator so that it will take what's called a program trace, a memory trace, model how that will work on a cache, see how frequently the accesses hit in the cache and how frequently the accesses miss in the cache, and print out metrics or statistics, tallies about how the cache did. So let's look at the test case for this part of the assignment. The test cases, again, are in the test directory. I'll pull up an example of that now. So here I'm opening one of the tests in the test directory. This file is called trace matmul 4x4. And this file is actually generated from a actual real matrix multiplication program. And using Valgrind, you can tell us to, while the program's running, record what memory addresses that program loaded and stored to. And so these lines of records, they record in the matrix multiplication program where it loaded from at the beginning, and each line is a memory access where the later memory accesses are farther down in the file. So these are ordered in time. And each line here, it records a memory transaction. So every line is going to start with a character. The characters are going to be either L, M, or S. So L means loading from memory. Store means, S means storing to memory. And M means a load followed by a store. It means modify. So that's what all these lines are. The second field in each line is going to be a memory address. So this number is a hexadecimal number. So you'll see here, for example, some of the memory addresses, they have hexadecimal digits here, right? So these are not decimal, these are hexadecimal. And these are the addresses that the CPU tried to access. And then the final field, this number 4 here, just indicates that this was a 4-byte access. And for the purposes of this assignment, you can ignore this final field. You can assume that all the memory accesses, they're all going to fit in neatly within cache blocks. Okay, so this is about the memory traces. As part of the assignment, there is an additional tool that we've given you. So that tool is located in the Programming Assignment 5 directory. And it's the program called csimref. So csimref is a program. It's a binary program that was compiled from some source code that we didn't share. And this program is compiled to run on x64, x86 64 Linux machines. And so generally speaking, this will only run on the iLab machines, unless you have access to some other Linux machine. The csimref, you can use it to simulate a cache. So it's basically a reference implementation that you can use to test your programs. So you can run csimref. It's an executable. So you can say /csimref. And when you run it, it'll print out this helpful message that tells you how to use csimref. And csimref wants to read trace files. So this file on the left here that I have an example, this would be something that you would feed to csimref. Csimref, so cache sim ref reference, that's what the name means. There's a bunch of options that you should use to control it. Most of the options relate to what size of cache that it's simulating. And so I'll give a demonstration of using csimref right now. And so for that, we need to know exactly what type of cache we're simulating in this first part. So if you read through the programming assignment description, I've given a discussion about what the input files look like. And for your task is to simulate a cache that has these parameters. Okay, so we'll input to csimref those parameters. So we'll say csimref, and then we'll go through the options, right? So we'll say how many set bits are involved. This is a fully associative cache, which means that there are exactly one set, right? The big S is 1. The number of set index bits is 0. So we'll say little s equals 0. The next parameter we have to give it is capital E, how many lines per set. The assignment description on the left here says capital E equals 16. Number of block offset bits equals 4, meaning that every time there's a cache entry put into the cache, there's going to be 16 bytes that are cached in one go. 16 bytes enough to fit 4 integers. And we tell that to the csimref reference program by saying little b equals 4 bits. And then it asks for a parameter that tells it what is the cache replacement policy. So remember, in this fully associative cache design, blocks would go into all the same set. And if the cache is already full, then it has to pick one of the entries to remove, to evict. And so here, for this part of the assignment, you're asked to do a FIFO cache. And to tell it to do a FIFO cache, we just say -L equals 0. So -L equals 0 is our next option. And finally, tell it what's the trace file. So I want to trace the matrix multiplication trace file that I gave you on the left side. So -T, and I'll point it at the test input, which is in the fully associative directory. It's in the test directory. And the test I want to do is trace matmul 4x4. We'll go ahead and run it. And the reference program prints out what you're going to be expected to print out, right? So you're going to write a program that copies the behavior of csimref, and its printout says that when it ran this program, the memory trace from this matrix multiplication program, when it runs on a cache that has these parameters, it's going to hit in the cache 196 times. It's going to miss in the cache, meaning that the request could not be serviced from the cache 12 times. And in the course of using the cache never filled up in a way that required any old data to be kicked out. So no evictions happened. An extra useful thing here is that csimref also has a verbose mode. So here it says you can say -v, which tells it to run in verbose mode. And so if you say -v, with all the same inputs, it now will go through each line of the input trace and say exactly what happened. So it'll do this line that says this memory access was a miss. The second memory access is another miss, and so forth. Right, so this printout should be helpful for you to study what's going on. So for example, if you're trying to work through an example on pen and paper, this should be a pretty useful reference. Okay, so let's go back to our slides just to check where we are. So I've given you a tour of the trace input and also a tour of csimref, which is a tool that you'll use to check your inputs. I see there's a question in the chat box. So Julio asks, do we need both csimref and test files to pass all test cases? Or all test cases are just given as an additional tool? So in other words, we only get full potential points with csimref and not passing all test cases. So I'm not exactly sure what you're asking here. Your grading is going to be again done with the auto grader. What the auto grader will do is again, it'll look at all the inputs in the test directory. It'll run your program against all of these test cases, and your program should print out the expected results, which you will find in the answers directory. Right, so the answers directory tell you what's the correct results. And if you look at each of these results, so for example, for the 4x4 example, the expected results already tells you that you're expected to print out these metrics. Okay, so this is all just kind of infrastructure for you to test your program, see what an example is. The verbose mode and csimrep is especially useful because it will run the trace and show exactly what happens with each line. Yeah, so csimrep is just a tool for you to study and to use as a reference.
Excuse me.
Sure.
So basically, csimref will give you the correct answer. It just helps you like see it more clearly, whereas the autograder just like runs it. You don't necessarily get to see like what specific each one should be. Like csimref just gives you a reference on what it should look like, and it will be something that will be helpful when you're thinking about how to implement or like what to write in the code, basically.
That's right. So if you run autograder, it's not going to give you, the autograder will just run your program against each of the test cases and say whether or not your result matched or not. And it may be helpful for you to use csimref to do a detailed simulation so that you see exactly what's expected each line. Okay, so just like in previous parts of previous programming assignments, I'm giving you some provided code. So let's look at the provided code that you should use to write your simulator. And so the provided code, for example, here it's already setting up the required cache parameters. That's all programmed in there. There's some suggestions on what data structures you should use to store the cache. And if I scroll down to the main function, a lot of the kind of grunt work of just reading files and reading the file line by line, this is all taken care of. The task that you have to do is to go into the access data function. Here is where you have to write code. So in the access data function, you'll have to study exactly what's going on and write the correct code so that access data simulates the fully associative cache. Okay. And so this general idea of you writing the code to simulate a cache, this is the same idea for all first three parts of this assignment. Good. So any questions up to this point? So yeah, like I said, hopefully this assignment, it's less about writing a lot of lines of code, but there is a kind of conceptual hurdle that you'll have to study through and make sure you really understand how caches work and to get all these tools to work together nicely. So Julia has a question here, parts 1 through 3. They all build on each other, but they're submitted separately. They kind of build on each other. Again, these are different cache designs. So while the general design general way that you're going to write the simulator is related. They don't necessarily all build on each other. Certainly, if you follow along with our discussion about caches, you'll know that set associative caches are a mix. They're a hybrid of fully associative and direct map caches. And so if you're able to do fully associative cache and the direct map cache, in some sense, the set associative cache is like taking the previous two, combining them together to create a set associative cache simulator. Okay. So that is where we are with the quick start on programming assignment 5. So what we'll do now is we'll do a quick review again of the cache design parameters. This should be primarily already been covered in lecture, particularly last week. But this time around, I'll try to tie the concepts to exactly what's happening in the programming assignment. And then we'll talk about new topics on cache metrics. So how well a cache is working, and then how to write C programs so that they work really well with caches. All right, so any questions still about assignment 5 before I launch into course material? So Sophia's got a question in the chat box. So the question is basically about why do we use malloc? So this is not exactly directly related to programming assignment 5, right? But you'll see that you'll have to use malloc again. So the point of malloc is that oftentimes you need to have data structures that have variable size. So before you actually run the program, you don't know how much memory it's going to require. And so you cannot write data structures of fixed size. And what malloc enables you to do is enables you to create data structures, arrays of variable size. And this is kind of a part of C programming that you have to do somewhat more manually. And other languages like Java, behind the scenes, like languages like Java and Python, behind the scenes, they are still doing malloc, but the those languages like Java and Python, they're taking off malloc and freeing on your behalf, but you do pay a cost in terms of performance, right? So if you write your malloc and free correctly in C, the performance would be better. Okay, caches. So again, several designs for caches here. You'll know how in assignment 5, you'll work through each type of these caches. The simulator, you'll be programming the different cache designs, the number of bits for the tag, for the set index, for the block offset to build each of the different cache simulator parts. And then what I'm going to talk about here is replacement policy, right? So one of the parts of assignment 5 is that you will implement a FIFO replacement policy and also a LRU, least recently used cache replacement policy. Just as a contrast, so for example, a direct map cache has exactly one line for each set, meaning that for any given memory access, it can go into exactly one place in the cache. And so for direct map caches, there is no need for any kind of replacement policy. If the cache set is already occupied and you try to access some address, and that address is not already in your cache line, then the existing line automatically gets kicked out. It gets evicted, so you can load in the new and correct address. This is what we mean. This is what we mean how direct map caches involve no replacement policy. Now, on the other hand, for both the fully associative and also the set associative parts of the assignment, here you need to have a replacement policy. The reason for that is that any address in memory that will get loaded into cache, once you find exactly which set, so which hash destination it should go in the cache, in that set, you'll have multiple lines. So you'll have several options on where that cached data or that block should go. And with this, if all of these are occupied, then when something misses, when one of the addresses misses, it comes in, you will have to have some policy, so some way to decide which one of these gets evicted. Right, so there's two general approaches that we will consider for programming assignment 5. One is called FIFO, where if you need to evict one of the lines from the cache set, you pick the one that was placed into the cache the longest ago. So essentially with such a cache set, you can model such a cache set as a queue. So it becomes a FIFO queue. And so that's why in the provided source code, I've given you a little clues that describe this approach as, that describe this kind of cache set as a queue. So essentially you'll have enqueue and dequeue functions to model the FIFO cache, FIFO fully associative cache.
Quick question, Professor.
Sure, go ahead.
When you mention enqueue and dequeue functions for that part, you don't necessarily mean that you need to write an enqueue and dequeue function, right?
Yeah, so obviously any way that you write access data that works will get full credit. But if you look at the provided code here, I've suggested to you that the data structure for a cache line, for this part, you can use something that looks like the linked list. So here you have the cache line data structure, a struct in C language. And in each struct, you have a tag to keep track of what memory address this records. And also associated to it, you have a pointer that points at the next cache line. And so this is hinting to you that you can model a FIFO cache replacement policy as literally a queue implemented as a linked list, and such that the data structure for the entire cache, this can be modeled again as a queue. So you'll have a pointer to the front of the queue, a pointer to the back of the queue, and a number to record how many nodes, how many items are in the cache. This is called the occupancy. And of course, you can get rid of all this, right? So if you can also choose to not use any of this provided code. There are, of course, other ways to simulate this this cache. Okay, so that's the FIFO queue. Sorry, that's the FIFO cache replacement policy for any kind of associative cache. Now, the other policy is called LRU, which is least recently used. And in this policy, you can imagine it's a little bit more complicated than FIFO. Essentially, the idea is that instead of just kind of naively evicting the cache record that is the oldest, you can keep track of which records are actually pretty useful, right? So if a cache record is very old, it's been in the cache for a very long time, but it still was recently accessed, then you probably should not remove that cache line. And instead, in this policy, you get rid of the cache line that was least recently accessed. And so you'll have to brainstorm exactly how you want to do this kind of record keeping. And in the programming assignment, you'll be asked to do a LRU cache replacement policy in the third part. So in the set associative part of this assignment, here you'll have a chance to practice using the LRU cache replacement policy. Okay. So any questions up to this point? This is about cache replacement policies.
So for the counter, do we just have like something that increments, or is that's basically what it is, or is it something else?
You can think about how you want to do it. So if we look at the provided code for set associative, so I'm opening the file in set associative directory called set associative provided. This is for the third part of the assignment. Here, I'm suggesting that one way you can do this is you can have a global variable called program counter. So program counter it reflects like the actual program counter in the program, right? So it keeps track of how many lines of code, how many lines of assembly code have been executed. And this program counter, I make it so that every time you read in a new line in the memory trace, this program counter increments. And then you can think about how you want to use that program counter inside the access data function in conjunction with your data structures that model the cache line to implement the LRU policy. Right, so the hint here is, we have a number associated with each cache line. So you'll want to somehow assign this number to the program counter. And then when you're trying to figure out which cache line to evict, you do a kind of a search across those cache lines. Good question. Okay, so again, we're talking about cache design parameters, right? So we've talked about so far how there's several pieces to describing a cache. The first is the placement policy. Is it set associative? Is it fully associative, and so forth? What are the size of the sets? What are size of the blocks, and so forth? There's the replacement policy, which describes which lines to get rid of. There's FIFO and LRU. And then the final kind of description of a cache is what happens with writes. Okay, so this is just to review kind of what we talked about last Thursday. In real caches, there are several policies here which talk about when you try to write from the CPU to the memory, what happens in the cache. So one approach is that when you write from the CPU to memory, you go ahead and pay the cost of updating the memory right away. A more complex design, but that would lead to better performance, is that instead of immediately writing to the memory, instead, you'll just keep the updated data in only the cache, and then only update the memory when that cache line gets evicted. Right, so this is trade-off between a more complex design that has better performance and a simpler design which has worse performance. Likewise, if you try to write from the CPU to the memory and it misses in the cache, right? So you try to write from the CPU to the memory and the cache does not contain that memory address. There's again a couple policies here that tell exactly what the behavior should be. So the first policy, one option is called no write allocate, which says that if you're trying to write from the CPU to the memory and it's not already in the cache, then forget it. Just go ahead and write to the memory and do not put the data into the cache. The more complicated approach here will be called write allocate. And here, the idea is that if you're trying to write from the CPU to the memory and it's not already in the cache, then go ahead and place that data into the cache. This is helpful because future accesses to that same location will hit in the cache. Now, overall, this is just for your understanding. This actually has very little to do with what we're trying to do in programming assignment 5. Right? So this doesn't really impact what happens in programming assignment 5. All you need to know is that there are these different policies at play when people implement real caches. Okay. So Eric's got a question here, or actually Sophia's also got a question, I think, which is related to this. So Sophia, if you could elaborate on your question, that would be nice. Let me look at Eric's question first. So Eric says, in write back, what if another thread wants to access the memory address that has not been updated in memory yet? Okay, so Eric's question relates to multi-threaded programming, specifically multi-core processors, right? So this starts to become a much more complicated topic, and this is kind of a big rabbit hole. This is a big trapdoor that leads to the study of parallel computer architectures, right? So this would typically be something that would be discussed in like an architecture 3 course, parallel computer architectures, where if you have all these caches, you have a CPU that consists of multiple cores, right? So here we have a picture of a CPU with multiple cores. Each of these cores, they have a cache, right? So they're keeping track of some copy of data that they are calculating on, their own little cache, their own little copy of the main memory, the program state. And you're implementing something like a write back policy, meaning that if a CPU if one of the cores tries to write to memory and it has a copy of that in its own cache, it'll only update its own cache and wait until later to update the main memory. And so now you have this problem where if you have multiple CPUs and they each have their own copy of the cache, their own cached copy of the main memory, how do we maintain coherence? So how do we make sure that they're in agreement on what the data state should be? So what's the program state? And then also another topic is called memory consistency, which is eventually when all that data gets written back to the main memory, how do you negotiate? How do you arbitrate between all of these different copies of data so that the program state is correct? Right, so all I can say here is there is another layer of hardware techniques called cache coherence and memory consistency that allows for CPU cores to each keep a local copy of what's going on in the main memory. Okay, If you're curious about this topic, the keywords to search are called cache coherence and memory consistency. Good question from Eric. Sophia's got a question here about writing to caches. So Sophia asked, I mean writing into cache, but not into memory, with the plan to transfer the data upon eviction. What if the CPU stops? And so, yeah, so that's related to what we were talking about here, right? So if you're only going to write the data to the cache, and then only when you're trying to evict that line do you update the memory, then if the computer stops, so if the computer power is off before updating to memory, then the program state will be lost. Right, so so the bigger picture here is what Sophia is really asking about is at what point does program data, so at what point does the state of a program really get written into permanent storage, right? So if your computer loses power, if it crashes, before the program state is actually written to non-volatile storage, right? So something like a hard drive or a solid state drive, then anything that's in the main memory gets lost. And so only when the main memory state gets written to permanent storage, like a hard drive or SSD, does that become kind of permanently updated into files and so forth, right? So this is really about the distinction between what's volatile versus non-volatile parts of the memory hierarchy. Good question from Sophia. Okay, so this is about write policies, this slide here. Again, this doesn't really impact what you're going to be doing on programming assignment 5, because there's nothing about these policies that you really have to simulate per se in the simulator. So Kevin's got a question here. Kevin asks, when a program loads, is it going to write a lot of useful information to the cache so it can run faster later? Yeah, so this is called cache warmup, right? And also another thing, okay, so cache warmup is basically this idea that when a program loads into a newly refreshed cache, freshly zeroed and everything, everything is going to miss. So we can look at the trace, right? So we can look at our programming assignment traces. And you will notice, for example, you'll often have this kind of behavior when the program first starts up. It misses relatively frequently before things kind of hit a more steady state, and there are more hits relative to misses. So when the program starts up, you'll always have a bunch of misses because there's nothing in the cache yet. And so after there's been some writes and reads to the cache, things start get loading and get loaded into the cache. Then the cache is then what's called warmed up, where it more frequently starts to be able to service requests to main memory. So that's this topic, this idea of cache warmup. So Xiaowei's got a question here. Again, back on the write hits and write miss slide. So Xiaowei's question is for write back eviction. is that like, say, when the cache is full and one new writing data coming from the CPU, one slot in the cache is evicted, and then it gets stored back to the memory address. That's right. So what do I mean by memory is updated upon eviction, right? So this question is really about when and how is the memory updated? So the way this works is that when the CPU tries to write to main memory and it sees that there is a copy of the data in the cache, then it'll go ahead and only write to the cache and then set a flag called a dirty bit. So it'll set a flag on that cache line saying that I've modified this line of data such that when this line in the cache eventually gets kicked out because the cache needs to be used for something else, only then is the data synchronized to main memory. So that's what we mean by write back eviction. Okay, so when we tie all these topics together, you'll see that real CPUs definitely use caches to deliver the performance that they have. This is all relating to the goal of creating this illusion of fast access to large storage. So the caches here enable this illusion that the CPUs have direct access to main memory, when in reality, that access is mediated through multiple layers of caches. And so you'll see that in a real CPU design, they'll have up to oftentimes more than 3 layers of caches, where the lower level caches, these are small but extremely fast caches. So here, for example, L1 cache only can hold 32 kilobytes, but it's extremely fast. So you can access data within 4 cycles of the CPU clock cycle. And as you move higher and higher on the memory hierarchy, so in the L2 cache, this is going to be a larger cache, but slower. Takes 10 cycles to access L2 cache. And L3 is even bigger and even slower. And so this illustrates this trade-off between speed and capacity. And we'll see that, so for example, in a real CPU architecture design, you'll have all these layers of caches and with these different types of parameters. Okay, so any questions here? So that's, again, just to review cache parameters, different designs for caches. And here on this slide, this talks about real examples of real caches. Okay, so again, that should be enough information to get through all parts 1 through 3 of the programming assignment. We'll next talk about some of the implications of caches, starting with different metrics relating to caches. And so you'll notice that in the programming assignment, your task is to print a single line that summarizes what happened in the cache. So there's these hits, misses, and evictions. So let's talk about these metrics a little bit more, right? So starting with cache hits. So cache hit, we've been familiar with this idea now. It just means that the memory location that you're trying to access has been copied into the cache. And so that request can be serviced directly from the cache. And so you can calculate this number called hit rate, which basically is the number of hits that happened divided by the total number of memory accesses that took place during the program. So that would look like, for example, if you just tallied up how many hits there are in this trace simulation and divide by the total number of lines in this trace. That would be the hit rate. And the nice thing is whenever you can service a request, a load or store to memory directly from the cache, it's relatively quick, right? So the cache is implemented in SRAM. It's physically close to the CPU. And so it takes only a few number of clock cycles to access the cache. And so that's why it's nice to try to service requests directly out of the cache. Now that contrasts with the opposite, right? So if the memory access cannot be serviced from the cache, this is what we call a miss. And so you can calculate a matrix, metric called miss rate, which is essentially the number of misses divided by the number of memory accesses. So again, if we go back to our simulated trace here, this would just be like taking all the number of misses like you see in the simulation and divide that by the total number of lines. That's the miss rate. And the penalty, so the reason that misses are bad is that it takes really long to service a miss. So if a memory request missed in the cache, it means that you have to instead go to the main memory to get a copy of that data. And that's very slow. So it takes upwards of something like 200 clock cycles to go service that in the memory. And so this is a large penalty to the program's performance. And one metric, this is just information here. So one metric that you can use to summarize cache hits and cache misses is this metric called average memory access time, which is essentially you take the time it takes to service a hit and multiply that by the expected value of how much time it takes to service a miss. So this is the probability of a miss and multiply that by the time it takes to service the miss. And this would be summarized as a metric called average memory access time. Okay. There's some more kind of background information here. So here, this talks about how, given our understanding of how caches work, we can take cache misses and classify them into different types of misses. So one is called compulsory miss. So this is what Kevin had talked about before, which is that when a program first starts up, the cache is empty. And so nothing will be put in the cache at that point. So everything misses. These types of misses are called compulsory misses because it just simply means that there's no copy of the data in the cache. Now, once the cache is warmed up, misses can then be classified into one of two types. One is called conflict misses, and the other is called capacity misses. And these relate to how you tune the associativity of the caches. So in conflict misses, this is like due to how these misses are misses because even if you had enough space in the cache, the way that the sets work and the hashing function works, it means that all of those accesses have to go to the same set. And as a result, you have kicked out the useful cache line because of earlier conflicts. These are called conflict misses. And the other type is called capacity misses. So these are just generally when the data misses in the cache simply because the cache is not big enough. And so the only way to address such misses would be to have a larger capacity cache. Okay, so in the chat box, I got a question here from Xiaowei. So Xiaowei's question is, this is cache wise, right? Yeah, so all of this is, so I think this was relating to the cache misses slide. Regarding average memory access time. Yeah, so average memory access time, this is as in how long it takes from the CPU to access memory, given that there's a cache, right? So sometimes they'll hit in, most of the times they'll hit in the cache, but in the few times that it does miss in the cache, you pay the penalty of having to access main memory. And so this leads to an effective time, an effective overall time it takes to access the memory, given that there's a cache. Okay, so that's relating to the metrics of caches. And this relates to the programming assignment in that your task is to print out such summary statistics. So you'll run through the simulation, count how many hits, misses, and evictions you see, and print out these metrics. Okay, so now into some interesting topics now. So the interesting things here are that you can actually try to write programs so that they work really nicely with caches. This is what we call cache-friendly code. And in the programming assignment, if we go to parts 4 and part 5, your task is to take programs for matrix multiplication and matrix transposition and optimize them so that they work better with the cache. And so in the programming assignment 5 directory, you'll see that there's 2 additional directories here called matmul and mattrans. These are existing baseline implementations of matrix multiplication and matrix transformation. And they've been written in a way such that they're not optimized to run on caches. And your task is to, in these directories called cache blocking and cache oblivious, to write better versions of matrix multiplication and matrix transposition so that the programs run better with caches. And so here on the left-hand side, I've opened up matrix multiplication, the reference baseline implementation of matrix multiplication. It's got a bunch of code that opens the test case files. And then what happens is it then runs matrix multiplication on the 2 matrices A and B and stores it in matrix C. And your task is to then optimize this so that this is more cache friendly. Okay, so that's just kind of a high level preview of how this relates to the programming assignment. And I want to explain here, so what does it mean for code to be cache friendly? And we'll give 2 specific examples in the form of loop interchange and cache blocking. Okay, so cache friendly code means that you've written your code, your program that implements some algorithm in a way so that you've maximized the probability that memory accesses hit in the cache, and you've minimized the probability that you'll have these costly penalties of misses and evictions. And so the insight here is, you can write, matrix multiplication is just an algorithm, right? So while the algorithm may be the same, you can still have different ways of writing the actual implementation of the algorithm so that they have different behavior in the caches. And a nice thing is that advanced compilers like GCC actually have a lot of functionality that automatically do such optimizations. So what I want to do here is I want to go to the documentation for GCC, specifically a page called optimization options. All right, so this is in GCC. You can pass to GCC different optimization flags. So there's several layers of optimization called O1, O2, and O3. And what each of these does is they do transformations on the assembly code. So they do transformations on how the source code gets compiled into assembly code so that it's better optimized for the architecture that the assembly code will run on. And so, for example, one of these optimizations that it would do is called loop interchange. So you can see here that enabling O3 optimization will enable this type of optimization called loop interchange. So if we look at loop interchange and see what the documentation has to say about it, it says that loop interchange does a type of optimization that takes source code that looks like this and turns it into source code that looks like this, right? So this example here, this is matrix multiplication, but it's modified the code in a way so that instead of doing the code up top here, it does code down at the bottom here. And so let me just give a really kind of hands-on demonstration of this happening. So I'm going to go to the matrix multiplication example. And I will have the matrix multiplication source code be written in a way that's done like this. So again, here's the matrix multiplication kernel, Cij equals Aik Bkj, right? This is just iterating through the two matrices so that you do matrix multiplication. And I'm going to have it so that the iteration indices are ijk. Actually, I'm going to have it so that it's an even slower version. So I'm going to go ahead and do matrix multiplication, but in the slowest way possible, right? So this is being done in a way so that this code is really unfriendly with respect to caches. Unfriendly in the sense that when you try to run this code, it'll very frequently not be able to service memory requests from the cache. And then I am going to compile this code. I'm going to go to the make file associated with matrix multiplication here. And you will notice that I've passed to it a GCC flag called -O0, which means let's tell GCC to not do any kinds of intelligent optimizations. So -O0, we can go look at the documentation here for GCC. It says optimizations completely disabled at O0. And so now we can try running this matrix multiplication. Again, I'm telling you to do this version of code here. I will make the source code. So now that we have a matmul program, and it is eager to take 2 input files to do matrix multiplication for us. So let's say matmul. I've got some test files here, matrix A, and the biggest test case here is a 32 by 32 matrix. It's 1,000 elements large. And I'll multiply that against matrix B, which is again a 32 by 32 matrix. I'll hit run, and it took a while, right? So this is the slowest possible implementation of this. Actually, I think you probably need to crank up the problem sizes for this to work even better. And then what we'll do is we will enable some optimizations. So instead of doing O3, instead of doing O0, I'll do it to do O3. Again, I'll make the source code. Let's see. Oh, okay. So interestingly enough, it actually also led to other compilation errors too. Okay, anyway, I'll rework this example here actually. The point being that as you turn up the optimization options, it will try to make the code more and more tuned to the specific cache parameters of the architecture that you're going to run the code on. Okay, so this loop interchange idea is that in part 4 of programming assignment 5, you will take the matrix multiplication example and you experiment with swapping the loop indexing around, and also try techniques like cache blocking so that you can see the impact of these types of optimizations on the performance of matrix multiplication, knowing that in practice, if you were to use optimizing compilers like GCC and tell it to use flags like O3, the compiler will actually do these optimizations on your behalf. Okay, so any questions up to this point? Okay, in the next few minutes that I have, I'll use the textbook slides, and I want to walk through the matrix multiplication example in a little bit more detail. So the idea here is we're trying to do matrix multiplication. And we're going to index the multiplication in a way so that the output matrix is always going to be indexed by I and J. And the two matrices that we're going to multiply together, matrix A is always indexed row and column wise by I and K. And matrix B is going to be indexed row and column via K and J. And so now, if we change the way that I, J, and K are iterated through, right? So the sequence in which I, J, and K are iterated, you'll actually see notably different performance in how well matrix multiplication runs. Well, so this is despite the fact that in all of these different versions really are all doing matrix multiplication. These tweaks in which how the program is written will have implications on the performance of the code. And all of this is due to whether or not the memory accesses can be effectively serviced by the cache. Right, so we'll go through one such example here, where we're going to do matrix multiplication, and we're going to index it so that the indices are I, J, and K, where we iterate through I first, so the rows of the A matrix and the rows of the C matrix. Then we iterate through J, which is the columns of the B matrix and the columns of the C matrix. And finally through K, which is the columns of A and rows of B. And the way in which that these different versions are going to have really different performance is if you look at the innermost loop. So this is the loop that's going to run the most times over the course of the matrix multiplication. And you can study whether or not this line of code is friendly with respect to the cache, meaning that is there good locality so that the cache can effectively try to service the memory requests more frequently from the cache. And so in this first version, I, J, and K, you will notice that the B matrix, we're iterating through K, which is the rows of B, meaning that in this line of code, we're going to be iterating through the elements of the B matrix in this tall manner where we're accessing multiple rows at once. And if you think about how this B matrix is stored in the memory, you'll know that accessing while the first element of B, and then the next row of B, and then the next row of B, all of these are going to have relatively poor locality, meaning that it has to skip through a lot of memory locations in the memory to access each of these elements. And so this way of implementing matrix multiplication here has really poor locality with respect to the elements of the B matrix. And so we can try to optimize this, right? So another approach to writing the matrix multiplication is that instead of iterating through the elements as we did before, here we're going to change up the way that the iteration is written. And this time around, you'll see that we're accessing the elements of the B matrix and the C matrix. And when we're accessing them, it has much better locality, meaning that we're scanning through the elements of the B matrix and the C matrix one array index at a time. And so here, the cache is much better able to service the requests to the elements in the B matrix and the C matrix in the innermost loop. Right, so this version of the matrix multiplication code is going to have better cache locality compared to the previous version. And so here they studied through several different versions. And the very worst version is here, where in this version, you have poor locality for both the A matrix and the C matrix because you're going to be scanning through the elements, each time incrementing the memory index by a whole column of elements at once. And so this has poor locality. And so we go through all these versions and you'll see that there is notably different performance coming from the matrix multiplication loop, innermost loop, depending on how you've chosen to index through the matrix. Okay, so this is just a real world example showing that writing your program so that it's better able to take advantage of caches will have real impact on how well your programs run.
So
Okay.
what? So caches work better when your thing's row major or something? Is it? I'm still confused.
Yeah, so essentially let's skip to like what's the best combination, right? So the best combination is Kij, Ikj, which is these two versions here, Kij, Ikj. And the commonality, so the common property of both of these approaches is that in the innermost loop, the scanning through the two matrices involved in this loop, right? So here it's going to scan through the elements of C and B, and they're being scanned using the array index J. And as J increments in this innermost loop, it's basically scanning through matrix B and matrix C, one column at a time, all within the same row. And so given what we know about how matrices are stored in the memory, each of these accesses will have good locality. You're always going to just be accessing the next element in the array, which is likely going to be in the cache already.
Oh, so they're stored just so they're stored like each column one after the other, and that's how it's stored in memory.
Yeah, so this ties back to, let's see if there's a good picture of this here. So for that, we can go back to our slides discussing that. The good picture to understand that and review that is that if we look at how data is stored in memory, how arrays are stored in memory, this picture here reviews how if you have a matrix that looks like this, then the data is stored in memory so that the elements in the same row, as you increment through the columns of the matrix, right? Same row, different column, they're stored sequentially in the memory. And then once you're done with the first row, then you store the second row, and then you store the third row, and so forth. And so that then relates to how you're scanning through the matrix for matrix multiplication. Here, as you scan through the columns, the elements are going to have good locality in the memory.
Okay.
Yeah. Okay, so our time is up for today. So we've talked about how the way that you arrange the loops in a matrix multiplication type of program will have implications on how well that program runs. But in practice, you can use things like GCC, the optimizing compiler, to take care of some of those detailed optimizations. It's able to identify such loops and automatically optimize for them. All right, so I'll take questions about anything that we covered today about programming assignment 5. Otherwise, thanks for dialing in, and I'll see you Thursday.
Excuse me.
Mhm.
So you mentioned how the -03 like that helps make the loop like more efficient, like with your example, like so if we were to when we do part 4, when we do the -03 and we run that basically just so like it would take like say what we currently have, like the unmodified version, which is slower. It will take that and it will run it as if it were the fastest version, basically. But then
Yeah,
we would still have to like figure out like that doesn't give us like any really clues in how to like which one is the fastest version. We would still have to like go into the code, like test it individually and then run it regularly, right?
so So a few things here. So in your program, you're not allowed to use -03 because we'll eventually overwrite your make file. So even if you use -03 and get this optimization, that's not going to exactly solve the problem. The specific task for part 4 of this assignment is you're still going to try to simulate the program trace and try to get what are the cache metrics. So what are the cache tallies for your program? So your task is actually to go inside cache blocking. And then in here, you'll go to the implementation in cache blocking provided.c.
Mm-hmm.
And the part that you'll be concerned about is in here, right? So you'll play with these different ways of doing matrix multiplication.
Okay.
And see if you can get a version of matrix multiplication such that the cache behavior in terms of how many times it hits, how many times it misses, and how many times there are evictions. You want to modify this so that it's better than the baseline.
Wait, okay, so what we need to do is we need to go and basically do what we're doing the other ones. We record the hit. We had to first go to the part that we had to first go to the part. This part right now, none of this does the hits, misses, and eviction. So we had to first basically write the code that does the hits, misses, and evictions. Once we have that down, we have all these different scenarios. We can just comment out and test, and maybe on the side we should keep like a written record, like which one has, and then when we compare it, we find one that has like the most hits, the least misses and stuff, and then we comment everything else out, leave that loop in, and then we can, that would be the correct submission.
Sure, right. So again, right, so if you run the auto grader, it takes care of, the auto grader will take your version here in cache blocking.c.
Mm-hmm.
It'll turn that into a cache blocking program. And then it will run Valgrind to get the memory trace. And then it'll simulate this memory trace and compare that against the baseline version. All that is being taken care of by the auto grader.
Wait, so in part 4, one part is basically testing this by commenting out like each of these loops and the other part is like, I think maybe above the main code where we have to wait. So this already does the hits and misses like for you, or
Right.
do it?
Right. So if you call auto grader, it will do the hits and misses for you. So it will go. It will just use the csimref reference simulator that's already packaged in there. It'll use csimref and test your program and see how many times it hits and misses.
Wait, so what part are we exactly writing in this part then? I'm confused now.
You're writing a optimized matrix multiplication here in cache blocking.c.
Okay, so like say we have this like, so we would go to, this is the cache box, so we would go to the matrix multiplication one, and then we should probably pull that, whatever that one, like if say it looks like JKI, for example, we would put that JKI in here, we'd run it, we'd see what it is, and then we maybe switch around to like IJK or IKJ or something like that.
Right.
So
and
basically,
see how those impact how many times you hit and miss, and then also potentially consider other optimizations as well.
so like both, we have to consider both possible loop optimizations and the possible and the other possible optimizations.
Yeah.
Okay.
So we'll talk about this more on Thursday, I suppose. But there's yet another set of optimizations that you can consider, which is called cache blocking. And if you want a preview of that, so cache blocking is also described in both the textbook and also in the textbook slides. Yeah.
Okay, thank you.
Good questions all around. All right. So yeah, I'll see you all on Thursday. Take care.